Hi. I'm Jim Heffron. These are my lessons in calculus too. So we've been doing techniques of integration, and we did some stuff that I think are hard. I mean, I think the trig substitution and the trig integrals are hard. There's some difficult algebra there, and the partial fractions. I don't know. I think it's a bit of a dog's breakfast. I mean, it solves a big problem, and a person needs to get it down. That's for sure. But it's a little hard. But we come to some topics now that are a little more fun, maybe a little bit of a payoff. So today's is one, improper integrals. So let's get started. Okay, let's see. So we're going to ask about involving infinity, which is always kind of an interesting thing to have happen. So here's an example. You toss a ball up in the air, and it gradually slows and then pauses for an instant. That's the stationary point, and then falls back. If you throw it hard, it'll go higher, but of course gravity keeps pulling, and eventually the ball slows down, stops, and falls back. Can we throw the ball so hard that it will never come back, and it never come back? I mean, you could throw it so hard it reaches the other side of the sun, but it nonetheless gravity keeps pulling. It never comes back. Now, obviously, I'm going to discount that you throw it so hard that it goes into orbit around Jupiter. So we're not talking about that. Okay, so is there an amount of work that we can do on the ball to make it keep going forever? Okay, so we need to counter the work done on the ball by the Earth's gravity. So I'm going to find the amount of work done on the ball in throwing it forever, forever. And work, of course, is a force of RdR. And the Earth's radius is, you have to sort of look this up in meters, 6,371,000. Okay, I did it in meters instead of kilometers because there's down here capital G is in meters, but it doesn't really matter. I'm not going to pay any attention to the units. Okay, so here I go. I know what the force is due to gravity, and we want to counter it. So we're going to figure out how much work gravity does on the ball in trying to pull it back to the Earth, and can we do more? Okay, so let's see. This is the limit is going to infinity. So obviously, what we want here is we want to find the integral from the Earth's surface up to r, and take the limit as r goes to infinity. All right, so the integral, we're getting pretty good at integrals now. So let's see, capital G is a gravitational constant. It's just a number, so we can bring it out past the integral. Lowercase m is the mass of the ball. It's just a number. We can bring it out past the integral sign. Capital M is the mass of the Earth. It's just a number. You can bring it out past the integral sign, and you're left with an integral here that is just 1 over r squared dr. 1 over r squared is not going to give us any trouble. The antiderivative is minus 1 over r, because when you take the derivative of this, you bring down the minus 1, multiply times 1, and it becomes a positive 1 over r squared. Okay, and again, the capital R and the radius of the Earth. And don't forget, when we're all done, we have to take the limit as capital R goes to infinity. So I plug in the capital R, plug in the radius of the Earth. There they go. Plugged in the capital R, plugged in the radius of the Earth. Because there's a minus sign there, you get minus 1 over r. But when you take minus 6,371,000, you're taking minus a minus, and it becomes plus, and that explains why it's here first. So that's not a typo. I did that right. Anyway, I'm taking the limit as capital R goes to infinity of this expression, and as capital R goes to infinity, of course, the 1 over r part goes to 0, and so oops. I forgot to put in the zeros there, and so we get a value that is finite. I mean, I don't really care what it is. Not going to worry about the units, for example, but it's a value that is finite. So the answer is yes. There is a finite amount of initial impetus you can give the ball so that it will leave the Earth and never come back. And again, I'm not paying attention to going into orbit around Jupiter. Just simply, can you just leave the Earth? I will say often people find this result counterintuitive. when you say to people, just the Earth is alone in the universe, and you throw the ball super hard, is it guaranteed to come back? And they say, well, no matter how hard you throw it, it's always going to be pulling, and eventually to pull it back, as most folks first guess. But that proves to be wrong. So a topic is kind of fun when it gives you answers that are the opposite of what you expected. So definition, if you have a is a real number, and you suppose that f is integral on the interval from a to b for b greater than or equal to a, I mean, this kind of stuff. The improper integral of f from a to infinity is, there we go, there's the infinity. The improper integral from a to infinity is the limit as r goes to infinity of the integral from a to r. This is a finite integral, so we've already defined what that is. And so now I'm taking the limit of a limit of a finite integrals. Okay, so we know how to make sense of the finite integral, so we now know how to make sense of the limit of those finite integrals, if that limit exists. Similarly, if you want to go not to positive infinity, but instead to the left, to negative infinity, not surprisingly, it's a limit as capital R goes to minus infinity. And if you want to do both, and we'll see example at the end where you want to do both. If you want to do both, you can break that at 0. Again, all provided that those limits exist. When the limit exists, we say that the integral converges. Otherwise, we say that the integral diverges. If the limit grows without bound, and we'll write plus infinity, and likewise minus infinity if that applies. But though still the plus infinity and the minus infinity are still divergent, they just diverge to, it's equals infinity we're taking as an abbreviation for grows without bound. Diverges because it grows without bound. Okay, so this is just a straightforward adaptation of the idea of the ball going up and up and up and up and up. So obviously time to do a couple. So here we go. X goes from 0 to infinity of e to the minus x, 1 over e to the x. Okay, so doing what the definition says, doing what sort of a good sense says, is that we know what it means to take the integral from 0 to capital R, and then I'll take the limit as capital R goes to infinity. So here's what it means to take the integral from 0 to capital R. Okay, and again, because of the minus sign, some things are changing place here. So that integral is right. I didn't flub up the signs. We know what it means to take the integral involving capital R, and now just take the limit as capital R goes to infinity. And obviously the 1 doesn't do anything. 1 over e to the r, so as capital R goes to infinity, e to the r goes to infinity, and so 1 over e to the r goes to 0, and when all the smoke clears, you just get 1. Drawing it as a picture, of course, this is a graph of e to the minus x. So I drew the picture here of the area under the graph from 0 off to infinity. Okay, so in this way, you can have a planar region that is unbounded, that has a finite area. Isn't that interesting? So even though the region is in some sense infinite, it still has a finite area. You could paint it with a finite amount of paint. Even though it goes off to the right, infinitely long, and infinity is a big place, it's a long way from here, it would take a finite amount of paint to paint it. Isn't that interesting? So kind of a fun topic. Also, I'll comment about the beauty of the result is that you take this picture, having a little trouble with my pen there. You take this picture and you think, well, it's kind of a complicated circumstance, and yet the answer comes out to be awfully simple. Okay. So just doing a second example, x equals 1 to infinity, and obviously I didn't want to do x equals 0 to infinity because it's 1 over x squared. So x equals 1 to infinity, 1 over x squared, and it's just going to be a straightforward application of what the definition says. So there I go. I know what the finite integral does. We're very good with finite integrals, and there it is. So we're very good with finite integrals, and now just take the limit as capital R goes to infinity. So as capital R goes to infinity, 1 over capital R goes to 0. So we're looking at 1 minus 0 and 1. And again, awfully nice result, 1. Awfully nice. And again, this is a region that is infinite in extent. You could just keep walking and walking and walking, and there's still more region to go. and yet you can paint it with, sort of 1 gallon of paint kind of thing. So an awful nice result. Okay, practice. So I recommend that what you do is you pause the video, give it a try, and we'll come back and see the answer. So I'll give you a second to pause the video. Okay, great. So here's the finite integral. X goes from -1 to r, e to the minus x dx. And when you do the anti-differentiation and you plug in and subtract, you end up looking at that expression there. You notice again that minus and minus makes plus. So you're looking at 1 over e minus, so that's 1 over e minus 1 over e to the r, as r goes to infinity. And of course, e to the r goes to infinity when r goes to infinity, so 1 over e to the r goes to 0, so we end up with simply 1 over e. Okay, another one here. The integral from 0 to infinity of cosine x dx. Okay, great. So here I go. Same thing I've been doing. I have an integral from 0 to capital R cosine x, and at the end I'll take the limit when r goes to infinity. So we're getting pretty good at these integrals. The antiderivative is sine of x. So you plug in capital R, plug in 0, sine of capital R minus sine of 0. I know that sine of 0 is 0, so I could cross that out and write 0. So I'm looking at the limit as capital R goes to infinity of sine of r, and we're seeing an integral here that does not converge, because it does not exist because it keeps oscillating up, down, up, down, up, down. So oscillates between 1 and -1. It doesn't settle down at a value. It keeps changing. So the limit doesn't exist. Okay? Okay, so another example, so like the prior example, this is like the prior example, the prior practice that we just did. So I'm going to look at 1 over x, x equals 1 to infinity, and again, I didn't look at 0 for the obvious reason. I started at 1. Off we go. The definition says take the limit as of the finite integral, and so I'm looking at x equals 1 to capital R, 1 over x dx, and then at the end you're taking the limit. And the finite integral, of course, where 1 over x is going to have an antiderivative of ln absolute x, but everybody's positive here, so I just wrote ln of x. And so I'm taking the limit as r goes to infinity of ln of capital R, and what happens to ln as capital R gets bigger, 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 and the answer is ln goes to infinity. I know it goes very slowly, but it doesn't matter, it goes to infinity. So this contrasts a little bit with the 1 over x squared case, in that this is again a region that is infinite in extent, but here the region has a sort of infinitely much area. It would take infinitely much paint to paint it. So we've seen now 2 in a row integrals that that diverge, but in particular this one contrasts with the example we did a couple minutes ago of 1 over x squared, which took 1 unit to paint. Now it takes infinitely much unit to paint for 1 over x. Okay, and we have a result that says where is the dividing line between those two. So if you look at 1 over x to the p, 1 over x to the p, x goes from 1 to infinity. And again, we're not looking at x equals 0 for the obvious reason. So x equals 1 to infinity. And what's the answer? And so the answer is, if p is greater than 1, you get a finite value. I actually gave you the finite value. And if p is less than or equal to 1, including the previous slide where p was equal to 1. So if p is less than or equal to 1, then you get infinity. Okay, I'm going to give the argument. We typically avoid proofs in this class, or just a question of not really our remit all that much, but we do take the opportunity to to talk to people who are, say, math majors or math minors, or people who are especially interested in the argument. So look at this, is just exactly what we were just doing. Here's the finite integral, and I'm going to take the limit as capital R goes to infinity. So x to the minus p, here's the antiderivative of x to the minus p. You write x to the minus p and then add 1 to the integral. and then write 1 over the number you just wrote. So there we go, 1 over the number I just wrote. Plug in the capital R, plug in the 1 and subtract. And when you do, there's I factored out the 1 over 1 minus p part. The 1 over 1, there's the 1 minus p part. So the 1 over 1 minus p part I factored out, and when I did, what was left was the limit as capital R goes to infinity of capital R to the 1 minus p, take away 1. So there's obviously there's a couple cases. You can see the cases up here in the statement of the result. So what happens to capital R to the 1 minus p? And the answer is, we saw earlier in the couple of examples that if you're looking at some kind of fraction, then with the variable on the bottom of the fraction, then you're going to find that the limit is 0. On the other hand, if you don't have a fraction, then you're going to find the limit is infinity. So let's have a look. If p is greater than 1, so that's the first case in the result. If p is greater than 1, then 1 minus p is negative. So if p is 7, then 1 minus p is negative. And so r to the 1 minus p, r to the 1 minus 7, r to the minus 6 power, for example, would go to 0 because it's a fraction as r goes to infinity. And so the limit converges to 1 over 1 minus p. Well, excuse me, 1 over p minus 1. Forgive me, I misspoke. The prior example, the prior slide, if p equals 1, then the prior slide shows that the integral diverges to infinity. So I did that as a separate case. And finally, if p is less than 1, that's this case up here. If p is less than 1, then, p is less than or equal to 1 is the case up here. If p is less than 1, then 1 minus p is positive. That includes, for example, if p is minus 50. So 1 minus p is positive. Capital R to the 1 minus p, so what did I say? P was minus 50, so capital R to the 49 power is going to go to infinity as capital R goes to infinity. Okay, so the argument is it's just really applying the results that we had and trying not to get twisted around about the 1 minus p power. So this is a nice result. This tells us what happens for a wide number of cases that we often run across when we're trying to solve these. So in addition to stating the result, giving the precise statement of the result, I want to give some intuition. So we saw that that the function f of x equals 1 over x, that the area under the curve is infinity. But with the other function f2 of x equals 1 over x squared, the answer is not infinite. The answer was actually 1, but anyway, the answer is not infinite. So what's the intuition there? How come the one and not the other? So the integral of 1 over x does not converge because the 1 over x function goes to 0 comparatively slowly, is the intuition. In contrast, 1 over x squared falls to 0 quite quickly. Now, just if you look at these boxes, I've put in the Riemann boxes, each with a base of 1. You're still seeing, you can see box there. You can visibly see that that's a box. But when you look at 1 over x squared, okay, I can see that's a box, that's a box, that's a box. But the rest of it just looks like line. 1 over x squared is racing towards 0 in contrast to 1 over x, which meanders to 0. So the intuition is that the integral converges if the function falls to 0 quickly enough. Now, of course, all this is not a proof. All this is hand-wavy, but nonetheless, it gives a person some sense of what's happening. So to reinforce that sense about how the one on the left is acting differently than the one on the right, I'm added up the Riemann boxes. I added up the first 10 Riemann boxes, the first 20, the first 30, the first 40, etc. And as you run your finger down this list, you see that those numbers are climbing. Now, they're not climbing super fast, but they're climbing. On the other hand, if you run your finger down the 1 over x squared list, and again, not a proof, but just to give some intuition, if you run your finger down the 1 over I squared list, those numbers, they don't really look like they're racing ahead. So 1 over x squared, you can see in both cases that you're getting an overestimate. See how you're getting an overestimate. But nonetheless, it seems that the numbers on the left are growing, and the numbers on the right don't have that same clearly growing sense. So the intuition is that the integral with an infinity on the top there, the integral converges if the integrand falls to zero quickly enough. And there's a point at which it's not falling to zero quickly enough, and that point is exactly, the transition is exactly the function f of x equals 1 over x. That 1 over x and, and any function whose power is smaller than 1 over x, don't fall to zero quickly enough. So 1 over square root of x, 1 over fourth root of x, sort of thing, don't fall to zero quickly enough. But 1 over x squared, 1 over x cubed, 1 over x to the fourth, they fall to zero quickly enough to make the integral exist. Okay, so some intuition. Now, a little bit vague and hand-wavy, but nonetheless, some intuition. It's about the rate at which the function falls to zero. Okay, so we did integrals that have an infinity sign in them, and they all seem to have a certain, goes the same way sense. So that's great. Next step up is to turn to another topic that is not really, it's something like the first topic, but it's also something a little different. So it falls into the same section only because I think that both parts involve infinity. Okay, so here what looks like an innocuous problem. X goes from -1 to 3, 1 over x squared dx. And I'm pretty sure that if I had a class that I gave this on the quiz, I'm pretty sure I'd see this answer right here on more than one paper. So the person is taking the antiderivative of 1 over x squared, looks good. They plug in 3, plug in 1, and subtract, and they get this for an answer, and they move on to the next problem. But they haven't noticed that there's something wrong here. 1 over x squared is a function that is always positive. 1 over x squared is positive, and because it says x squared, even when you put in negative x's, you're still getting positive outcomes. So 1 over x squared is always positive. How can the area under the curve be negative? That doesn't make any sense. We did something wrong. So what did we do wrong? And the answer is that, look at the graph here. I got the computer to draw the graph. Is that there's a place here, right here, where the function is not defined. So we blithely ignored that when we did this. So that's why I called it a naive approach, because it didn't pay attention to the fact that there's an infinite discontinuity there. Okay, so we have to learn how to deal with those. So to avoid the input where the function's undefined, what we're going to do is going to break the integral into two integrals. We'll take the integral from -1 to 0, and then we'll take the integral from 0 to 3, same integrand. I'm going to evaluate the integral from -1 to 0 by taking the limit. I'll take the integral from -1 to capital R, see how this is like the stuff we have been doing so far, as capital R goes to 0, from creeping up from the left, creeping up from below. And this is all, again, looks like the stuff we've been doing so far here. And you take the antiderivative, you plug in capital R, plug in -1, you get an expression. And you say to yourself, what happens when R goes to 0 from below? So if R goes to 0 from below, the fact that R is below 0 makes this expression here be negative. Okay, all right, so that cancels with this negative here. But more importantly, when R goes to 0, either from above or below, 1 over R goes to infinity. So the whole thing about the signs, the S, I, G, and S, meant that this going to positive infinity, but in any event, it's going to infinity. So this limit here, oops, I stopped my expression in the wrong place. This limit here does not exist. Specifically, it diverges to infinity. All right, so on the prior slide, the area under the curve to the left of 0 is infinite. This area right here. This area right here is infinite. So only paying attention to the negative part of it. So that part's infinite. So when I broke this integral as a whole up into two halves, the left half is infinite. So the left half doesn't exist. How can you add something that doesn't exist? So we're going to call the whole thing. We're going to call the whole thing D and E. Okay. All right. So of course we need to write this down. So if you have if the function is discontinuous at b, but continuous on some interval that works to the left of b, then when you have an integral that says a to b, you're going to look at a to capital R and take R approaches b from below. So it should remind you of the infinity case. Similarly, if you have a function that is defined to the right of b, then you look at the finite integral capital R to a, and you take capital R goes to b from above. So you creep down to b, provided that the limit converges. As to both sides, if f has an infinite discontinuity, some c where in the interval where the function is not continuous, but is continuous elsewhere in that interval, then you can break the integral up into two different cases, a case to the left of c and a case to the right of c, but you got to have both integrals have to converge, both to the left and to the right. If one of them is plus infinity and the other one's minus infinity, they don't cancel, nothing like that. Both integrals have to exist. Okay, so we're obviously going to do an example. So let's see, 1 over x to the 1/2 power from x equals 0 to x equals 3. So I look at I know that the problem is when x is 0, and I look at the finite integral here, x equals capital R to 3, and I'm approaching 0 from above. So I'm creeping down towards 0 with capital R. So we've done a number of these now, so I feel pretty comfortable about it. You do inside the parentheses first. That is to say, you antidifferentiate first, plug in the 3, plug in the capital R, it gets you an expression. Now, look at that expression and ask what happens when capital R goes to 0 from above. So if capital R goes to 0 from above, then the square root of capital R is going to 0 from above, and so we end up just with 2 radical 3. Okay, so this looks like the problems earlier from infinity, but in some sense they're very different. Okay, and again, I urge you to stop the video, pause the video, and try the problem, and then you come back and you'll see the answer. Okay, so I think this should remind a person to look exactly like the previous problems. So the difficulty here is with this first problem is what happens when x is 0. So we have capital R to 3 instead of 0 to 3, capital R to 3, and we're going to take the limit as R goes to 0, in this case from above. Take the antiderivative, so we're doing inside the parentheses. Take the antiderivative, plug in the 3, plug in the capital R, and ask what happens when R goes to 0 from above. So what happens to the part that changes? Well, if R is going to 0, if R is 1/2, 1/3, 1/4, 1/5 like that, then 1 over 1/2 is 2. 1 over 1/3 is 3, 1 over 1/3, 1 over 1/4 is 4, etc. So we're looking at infinity. Okay, the minus and minus makes a plus, but it doesn't really matter, but it turns out to be positive infinity. But in any event, it diverges to infinity. So the limit does not exist here. Okay, second problem, just simply practicing the problem, that's all. Okay, great, and again here a person notices the trouble is at 0, so I'm going to look at the finite integral from minus 2 to capital R and approach 0 from below, from the minus side. Okay, fair enough. Antiderivative of 1 over x is ln absolute x. Here I didn't drop the absolute because the numbers are negative, so I need the absolute. Plug in the capital R, plug in the minus 2, and subtract, and ask yourself what happens when capital R goes to 0 from below. Ln absolute capital R. So you need to remember what ln looks like. Of course, the absolute value means that what ln is seeing is positive numbers. And so I'm feeding values that are closer and closer to 0 to the ln function. And there's an ln function being fed positive numbers. And the numbers will be positive because it says absolute value. So when you feed ln positive numbers that are closer and closer to 0, of course, you get an outcome that is closer and closer to minus infinity. So the limit here diverges to minus infinity. Okay? I have a couple topics that I want to talk about with improper integrals. So this is just kind of a little extra discussion of using these because, again, I feel like we did some hard work so far, and it's nice to have a payoff. Okay, first topic, Gabriel's horn. So we have already seen Gabriel's horn. You consider the region under the curve f of x equals 1 over x, and you rotate that region about the x-axis, and you find the volume. Now, sometimes folks have a little trouble with three-dimensional stuff, so I have a three-dimensional picture. I hope it cooperates. Let's see. So there, I drew the three-dimensional picture, and there we go. You can see when I rotate, you can see that it does look like a horn. The person blowing the horn is down here at positive infinity, but anyway, it does look like a horn. Inside the horn is the graph of 1 over x, and there's in the middle, you can see a slice. That's a disk. Okay, so that's that particular shape just goes by the name of Gabriel's horn because generations of calculus students have looked at it, so it has a name. Okay, so we're back now to looking at the 2D version. When you use the method of disks, then you're looking here at limit as x goes from 1 to infinity. There's the 1 right there. Limit as x goes from 1 to infinity, pi r squared. That's the method of disks. So there's pi and there's r squared. I brought out the pi just to get it out of there, and we know how to do an integral that has infinities in it. You do the limit from 1 to capital R, and take the limit as capital R goes to infinity. So I'm doing the limit as plugging in the there's the antiderivative. I got to plug in the capital R, plug in the 1 and subtract, and then take the limit as r goes to infinity. Okay, and as r goes to infinity, 1 over r goes to 0, so we're looking at a limit of 1. Don't forget the pi out here, so we end up with a total volume of pi. And again, that's awfully pretty result because you have a kind of a complicated circumstance, and turns out the answer is, pi. Now, at the start of the slide deck, we saw a couple of two-dimensional unbounded regions with finite area. But what we've just seen here shows that there are similar regions in 3 dimensions. You can have a region that is unbounded in the sense that you could just walk here, just walk to the right, and just keep going forever and still be inside the region. You'd have to start ducking at some point, but anyway, still be inside the region, and it's unbounded in that way, and yet it has a finite region with finite volume. Okay, so if before it was 2 dimensions, so I painted something with paint. Here, if you came with 3.14 many paint buckets and poured them down the horn, you would fill up the entire horn. Okay. So again, awfully nice. Nice to have a kind of a fun result. I have two more applications of these infinite integrals. I sometimes have folks in this class who scoff a little bit about the infinities. So I just want to do a couple of results that indicate that people who work in these sort of applied areas, they think in this way. So I have an example. So people from around the world are going to click on our YouTube channel. So, at any hour of the day or night, somebody could be clicking on it. Somebody in Malaysia could be clicking on it at what is my 3 o'clock in the morning. So the money is coming in sort of at a steady stream. The money doesn't actually come in, but you can imagine the money came in at a steady stream 24 hours a day. So the most natural model for that is a continuous stream of income. Suppose that we get from our YouTube channel $10,000 a year. And again, I urge you to note that we do not get $10,000 a year. But anyway, just for a round number, imagine we get $10,000 a year. Current market interest rate is 5% per year, meaning that the money next year is worth less than money is today. If somebody said to you, I'll pay you $10,000 in a year, you'd say, well, but I'd rather have it today. I could borrow money today and end up with $10,000 kind of stuff. Okay, so we have to discount future payments to their present value. Okay, so for instance, receiving $105 a year from now is worth the same as receiving $100 today. So find out how much the channel is worth today. So I got to discount here at the back the value of the money at at each year, but I'm going to somehow add up all the $10,000 a year forever. Okay, so if we were not discounting to the present value, then in a tiny fraction of a year, dt, let's say dt is 1/5,000th of a year. Okay, so we would make 10,000 times 1/5,000th. But at the time t, the value of the money is not 10,000, it's 10,000 discounted to its present value. So 10,000 over e to the 0.05t, that's PERT, e to the RT. In short, so we accumulate a stream of income by discounting continuously at the market rate. I make the 5% up, but it's something like the market rate at the moment that I'm talking. So I want to add up, I want to accumulate the continuous quantity of money coming in, but noting that the money coming in a year from now is worth less than money coming in right this minute. So the discounted to present value money coming in, and I'm adding it up, I'm accumulating it forever. So of course now we're down to the mathematics. The mathematics says to take the finite integral and then take the limit of that finite integral as r goes to infinity. So I don't think the finite integral is all that tough a problem. So you plug in capital R, plug in 0, and you take the limit as r goes to infinity, and I'll spare you the algebra. You end up with $200,000. Okay, so just because the money comes in forever doesn't mean that the stream of income has infinitely much value. So just like we had these regions in the plane or in 3-space that were infinite in extent and yet not infinitely large, so too we have this stream of income that goes on forever but is not infinitely valuable. You know, when you buy a stock, you can imagine that the stock is going to pay you a dividend of $10,000 a year, let's say, forever. And you say, well, how much is the stock worth? And the answer is not infinity because it pays forever. The answer instead would be, in this case, $200,000. Okay, so again, the point is that people who work in this area think this way. Think with the infinite accumulation. Okay, one more example of the same sort of thing. So we're going to select at random a specialty fluorescent bulb, and we're going to run it until it fails because we want to test it to see what's the life. Is it? We took it off the assembly line, and we're saying is the assembly line testing out correctly today? So what's the chance that the bulb lasts between 1 hour and 10 hours? So for discrete probability, the kind of probability most folks are typically used to coming into this class, like dice or cards, with each outcome you associate a number. That's the probability of that outcome. But this is a continuous situation. The bulb could fail at any instant. So for each potential outcome t, if I said 1.704962 hours, I get a number f of t that's not a probability. Instead, it's a density. It's a rate. So fluorescent bulb life follows the formula f of t is lambda e to the minus lambda t. That's just simply a fact about fluorescent bulb life. I pulled that out of an engineering specification. That's just the way they work. So what I get here, I drew a graph of f of t equals lambda e to the minus lambda t. I drew a graph. There we go. And I've got the area under that curve. Area under that curve up to time x. So what's the chance that the bulb lasts between 0 and x many hours? And the answer is the integral from 0 to x of the density function. Okay, so I use t here for the dummy variable, and I'm using x for the function variable. So this underlines that something that we've talked about a number of times here, that the values of f on the graph are not probabilities. If I say to you something like, well, for t equals 5, f of t is 0.01, that does not mean the probability of 5 hours is 0.01, because then you'd be adding up infinitely many finite values, and this gold area would already be infinite. That doesn't make sense. Instead, f of t is a density. Okay, so F tells you somehow where F is high, there's more kind of probability stuff. And where F is low, there's less kind of probability stuff. This probability stuff is less dense. So this might remind you of the thin rod, where parts of the rod are very dense, parts of the rod are not dense at all, and you want to total it all up. Okay, so a probability density function, F, has the properties that it's got to be positive, because you can't have negative probability, and it's also got to be the case that if you integrate over all possible numbers, then you get 1, because probabilities have to somehow accumulate to a total of 1. So that's called a probability density function. Our particular bulb, I'm making this up, of course. Our particular bulb is manufactured in such a way that lambda is 0.5. That's just a question of you look up the specification sheet in the book that the vendor provides, and it says lambda equals 0.5. And you ask yourself, what's the chance it lasts between 1 hour and 10 hours? And there we go. There's the density function, t equals 1 to 10, and I brought out the 0.5 just to get it out of there. That's all. E to the minus 0.5. Take the antiderivative, plug in 10, plug in 1, and subtract, and the answer comes out to be about 0.6. Okay. What's the chance that the bulb lasts more than 10 hours? Now this is an infinite integral. So I'm going to handle it like we handled all the other infinite integrals. There's the density function, and t equals 10 to infinity means that I'm taking the limit as capital R goes to infinity of the finite integral. The finite integral is not particularly a challenge for us. You plug in the capital R, plug in the 10, and subtract, and the answer turns out to be about 0.007. So this area right here is about 0.007, pretty small. That's not tenths, that's not hundredths, that's thousandths, 7/1000ths, 7/1000ths. Okay, so we can answer questions about these bulbs by using integrals that involve the symbol infinity. Again, here our probability density function has to satisfy the property that f of x is greater than or equal to 0. That makes sense. And also the property that if you integrate over all the relevant inputs, then you get a value of 1. So I'm going to close here with I have a probability density function that is made up of 1 over 1 plus x squared times a constant, and the question is, what's the constant? Okay, and the answer is that I've got to have it be the case that if you integrate over all relevant inputs, you have to get 1. Okay, so I know how to integrate from 0 to infinity. Here we go. There's the finite integral. Take the limit as capital R goes to infinity. And when you, I brought the c out just to get it out of there. When you do the trig substitution here with tan theta, you end up with you end up with an integral that gives you pi over 2, c times pi over 2. So the answer is, to get 1, c has to be 2 over pi. Okay, so again, just trying to bring forward here that I sometimes have folks have a reaction to this section of the course. They say, well, but these infinite things, they sort of aren't really real, but they are real. This is how a person, in this case, illumination engineers, but anyway, this is how a person answers questions about about things that happen sort of in life. Okay, very good, very good.